Hello guys, today we are going to review another one of the paper written by Anjan A. Sen, Shanawaz A. Adil and Somasri Sen, in which the title of the paper is Do Cosmological Observations Allow a Negative Lambda? So this paper is linked with the Hubble tension, which you already know that when you are trying to measure the Hubble in the high redshift region or low redshift region, there is a discrepancy in the value of the Hubble parameter. So in this direction, they have defined something that can cosmological constant be negative value. So we are going to understand that what is this paper all about, and this paper is giving you some idea that how the universe may look like if we employ this kind of uh, cosmological constant which can take a negative value, whose energy density can be negative, and we can also see that is this also possible or not. Okay, before we are going to start our paper, let us just first read the abstract. In the view of recent measurement of H0 from the Hubble Space Telescope and supernovae H0 for the equation of state SUS team, we explore the possibility of existence of negative cosmological constant, means that anti-de Sitter vacua in the dark energy sector in the universe. In this regard, we consider quintessence field on top of the negative cosmological constant and compare such construction with lambda cold dark matter model using different combination of cosmic microwave background. Type I1, type Ia supernovae, baryon acoustic oscillation, and H0 data. Various model comparison estimators show that quintessence models with negative lambda are either preferred over lambda CDM or perform equally as lambda CDM model. This suggests that the presence of negative lambda ADS ground state in our universe, which can naturally arise in string theory, is consistent with cosmological observations. So from this abstract, we can understand that they have tried to develop a dark matter candidate on the top of the anti-de Sitter vacua space. What is this all about? Meaning we already understand that incorporate this accelerating expansion, we have the best model, which is lambda CDM. Means lambda is the cosmological constant and CDM for cold dark matter, in which we have G mu nu is given by the Einstein tensor, and this is written as kappa square or whatever the Planck inverse of Planck mass into some, let us say, T mu nu, and T mu nu has the energy tensor whatever the component that is present. Now, if you apply that, okay, the universe is homogeneous and isotropic. It means that it does not have any preferred direction or orientation. The metric that is called Friedmann metric is usually written as minus dt square plus some scale factor which is time dependent, and we are working in the flat region. So if you are employing this and with the G mu nu, you will get two equations. First of all, you are getting 3h square is equal to kappa square and whatever the energy density which is present in the universe. Now in this case, we usually have the radiation in our universe, then the matter density we have in our universe, and if you're working with the lambda CDM model, we can say that okay, there is some constant density which is depicted as our dark energy density. So if you are working with this kind of model, then we can say that okay, we can define such pressure. Let us say if you have the rho r and rho m, the pressure of rho r is 1/3 of this one. Pressure of matter is turning out to be 0, pressureless, and pressure of this lambda is turning out to be minus of lambda. So this minus of lambda is giving you the equation of state. So basically P is equal to omega times rho, and this omega is called equation of state. So for the cosmological constant or any vacua that is present in the universe, which is responsible for the dark energy kind of characteristic or repulsion kind of thing due to which the universe is accelerating, so omega is usually given as negative of -1. Now, there are so many alternate theory of lambda CDM. In lambda CDM models, the equation of state is just -1. So there are different kind of models that you can work with. For an example, we can work with the quintessence as well as kssense, tachyon, and maybe some holographic dark energy and different kind of scenario that is present, in which the omega is dynamical. It means that omega can depends on based on the, let us say, quintessence is given by phi, or maybe quintessence is given by x and phi. Similarly, tachyon is given by x and phi. So omega can be depending on phi or any field variable or x. Now, because of this field dependent, it is more dynamical than lambda CDM model. And when we try to test these models against the cosmological data, it is found that universe is preferred to be more or less lambda CDM model. So all these models, quintessence, k-essence, tachyon, actually fall in the category of this lambda CDM model. But when they are minimally coupled, and when we are saying that these are minimally coupled, it means that when we are writing the equation d4x square over minus g r over 2 kappa square, where r is the Ricci tensor or Ricci scalar, and plus when we are adding some matter equation. So this matter equation or matter action can be written as d4x square root of minus g, some Lagrangian. Let us say we are talking about the quintessence f and d mu phi. So when these kind of things are there, when there is only gravity portion is coming from this metric. So when any matter field which is coupled with just square root of minus g, where g is the determinant of the metric, then these are called minimally coupled. Now in the lambda CDM or quintessence or k-essence or any tachyon kind of field, and when they are minimally coupled and when they are tested with the cosmological data in the high redshift and low redshift region. For an example, the low redshift region is considered to be, let us say, 1 or 5 between from present in the present case z is equal to 0 and the past case z is equal to 5, or in the high redshift where this is corresponding to 11,000 and from present. So there are two categories in which we are, so there are some bow data, so baryonic acoustic oscillation, in which we are trying to see the spectrum from the galaxies and all these things, in which there is a matter and there is a perturbation of matter, and from which we can constrain it what is the density of these matters and so on. And whenever we are trying to incorporate the high redshift region data, in which we are talking about the cosmic microwave background. So this is the radiation energy in the universe, which is due to the last scattering state, in which after the Big Bang, after when the Big Bang had happened, and after the Big Bang of 38,000 years later from the Big Bang, the photons has decoupled from all the different components which were in the universe, and the universe has cooled down enough. So from there, all the photons has decoupled and stream in the all direction of the universe. And when we have captured this captured these photons, and their temperature is more about 2.7 Kelvin, and they are falling in the region of microwave. So they are called cosmic microwave radiation or cosmic microwave background radiation, whatever you can call. So these are just giving you the introductory thing that what's going on, how we can say that what is minimally coupled, what are the fields, what is lambda CDM model, and what are the components that is living on this thing. So whenever you try to measure this Hubble parameter, let us say 3h square is equal to kappa square rho m, and when you try to incorporate with the data, that you are finding that when you're measuring, it turns out that in the CMB data, when you are doing the measurement, it turns out that it is approximately 67 kilo per second, so on. And when you are measuring in the low redshift region, it is turning out that it is giving you the 74. So there is a huge difference between the measurement in the different data sets. So now what else we can do? Well, there can be, you can construct many type of different fields, and you can say that maybe this field can depict as a dark energy. But again, we have limited amount of sources. There are a lot of theories which from the string theory and different theories, from which we try to frame that okay, this field can can reduce the discrepancy of Hubble tension and so in a significant way. So the other way to do it without using any field, we can understand that in lambda CDM, the omega is just constant. In the other case, when we can say that okay, dark energy And during the early phase of the universe, dark energy was very insignificant. It's approximately zero. And during the present time, dark energy, the universe is dominated with the dark energy. So what we can say that, okay, this equation of state of dark energy is maybe dynamical, and this dynamical shows from the scale factor, that if we can say that, okay, omega is a scale factor, so maybe we can understand. So the omega can be depend on a scale factor, or maybe it can depend on the redshift. And this redshift and scale factor is given by this. So they have 1-to-1 relation. A is equal to 1 over 1 plus z. So whatever you can choose, it can show the dynamical feature. So instead of working with different amount of field, and you don't know what could be the best candidate to represent dark energy, we can parameterize the omega a, and we can use the Taylor series expansion around, let us say, omega naught at a is equal to 0, a is equal to 1, because at present we can say that a is equal to 1. And we can say that, okay, this is could be like omega a and 1 minus a. And this kind of parameterization is called CPL parameterization. And this omega 0 is again constant, omega is also a constant, and 1 minus a, this 1 minus a shows that this omega a is dynamical. So we can, from here you can see that as z is increasing very high, greater than 1, a becomes very lesser. So it means that when a is very near to 0, we are talking about the past epoch. And when z is equal to 0, which is showing the present epoch, it means that a will become 1. And for z is equal to minus 1, it is showing you the asymptotic future of the universe. So a becomes again infinity in the positive direction. So in some sense, you are going from 0 to infinity, from past epoch to future epoch of the universe. And in the mid of it, a is equal to 1, give you the present scenario of the universe. And when you try to measure all the measurements, we are measuring everything from past to the present. So we don't have much idea about what will happen to the future, but based on the dynamics which is shown by the data in the past, we can say that, okay, maybe whatever the trend it is, the future will also follow the same trend of the past. But we are not. In order to remedy this Hubble tension, there are different things can happen. It means that they are showing that there could be interacting dark energy models. It means that in the present state of the universe, the radiation density is extremely low, and the universe is dominated by either dark energy and dark matter. So dark energy is approximately 70%, and dark matter is approximately 27%, near about. And rest of the 4% of energy, or 3 or 4% of the energy, is what we are made up of. And these matter are the pressureless. It means that they are not exhibiting any pressure. So whatever the negative pressure that you are encountering from, it's solely from the dark energy. Okay. So now the problem is that when you are introducing the lambda CDM model, this lambda CDM model is happen to be always positive in the present scenario. Okay. So that when we are writing the pressure, is P is equal to minus of lambda, and lambda is happen to be greater than 0. Now, why is that? Because we understand that, whatever the universe is made up of, the energy density cannot be negative. So energy density has to be positive. Therefore, we are introducing that the lambda, we don't know what it is, has to be the positive energy density, so that our universe will not collapse. For the physical universe, it has to be this one. So this type of cosmological constant is falling under the study of De Sitter. So this is the De Sitter space, in which we can say that h dot, the variation in Hubble parameter, is nearly 0, means that Hubble is constant, and then it can be given by h is equal to a dot by a, and h is nearly constant. So I can just write a dot is basically dA over dt, and there is a a. So I can simply construct that, okay, I can take the integration h into dt, taking an integration dA over a. So this would become s times dt, and this would become log of a. So a becomes e of ht, and a cannot be negative. So the argument of this exponent is always positive. So it's from 0 to infinity, and scale factor is always increasing. Okay. So that is the concept of De Sitter, that whenever you have the lambda CDM model and the energy density of lambda CDM is turning out to be positive, then we have the h is nearly the variation of the h is approximately constant, There is no change in there is no any variation. So H is equal to A dot over A, and scale factor, you can see that scale factor is that how the universe is increasing. So as the universe will increase, the scale factor is also increasing. So here you can see that as the time will go, scale factor is exponentially increasing. So the question arises that, okay, how far it can increase? So we don't know yet at how far it can increase, or there will be some contraction of the universe in the future epoch. We don't know yet. So, but what is the anti-de Sitter? Now there is a de Sitter space and there is an anti-de Sitter space. And anti-de Sitter space is basically anti-de Sitter space, whatever. The energy density of the vacuum is negative. So whenever you have the energy of the vacuum is negative, then we have anti-de Sitter space. Now you can see that if the lambda is turning out to be negative, then pressure would become positive, because the equation of state demands that P is equal to, the equation of state is negative of 1 and lambda is negative, pressure is positive. So it cannot be possible that there will no expansion. What they have figured out in this paper, they said that do cosmological observations allow a negative lambda? So we understand that if you are just incorporating lambda just like that, lambda cannot be negative. That is the clear. So what they have done, they have said that, okay, there is a vacuum in our universe, and on the top of the vacuum there is a field that is living there. So this field can be quintessence type or anything, and since quintessence type is extremely simple, so they have assumed that there is a anti-de Sitter space which is filled in the universe, and this anti-de Sitter space, the energy has to be negative. While adding any field, for an example, let us say quintessence kind of field, you are adding one more candidate top of this, means that there is a vacuum still there, and there it is, you have phi. Then what is the advantage? So when we are writing 3h square is equal to kappa square, let us say rho radiation plus rho matter plus rho of lambda. So if you are not adding anything, let us say rho lambda is the de Sitter space or this cosmological constant, you can see that this has to be positive, this has to be positive, and this has to be positive. Okay, and now if I am normalizing everything, we can say that, okay, this will become kappa square rho r over 3h square. So whatever this factor is, I can just write over omega r plus omega m plus omega lambda. Okay, so I am normalizing it. Now you can see that everything, whatever over here, everything is contributing to 1. So I can always write omega lambda is equal to 1 minus omega r minus omega m. So these are all the things are constant, all the things are greater than 0, so omega lambda has to be 0. Now the liberty introducing, so omega lambda is, we can say, let us say it is a dark energy, and this dark energy must be positive. Now this dark energy, they have said that, okay, this dark energy is made up of two things. One is the omega lambda and one is the omega of any kind of field. Now what happens? Now this omega density has to be always lesser than 1 or equal to or greater than 0 and lesser than 1. So now they have extra degree of freedom. Now suppose that omega lambda is minus 5. Then in order to make it 1 or whatever it is, the omega phi has to be 6. So it means that now you have the liberty. Now suppose that if you were working with, in this scenario, there is no any liberty here. Omega lambda has to be between 0 to 1, and because of that the equation of state will always fall in negative of 1, and because of this the Hubble parameter cannot exceeds, we cannot when we are measuring the Hubble parameter H0, it cannot arises, it cannot go beyond 67 kilometer mega per second, so on. Okay, but when you have cosmological constant or anti-de Sitter negative thing, now you are increasing the field density. And what is the very interesting thing happens when you are increasing the field density? So when you are increasing the field density, therefore the equation of state or the pressure that is imposing by it will also increases. And because of this increment in the pressure, the equation of state now can go beyond -1, and this implies that we can increase our Hubble parameter. When you are measuring the Hubble limit or Hubble parameter, it can also exceed. Okay, so that is the idea. So if you don't know about quintessence, I have made several videos on the quintessence. You can say that the quintessence energy density is turning out to be half phi dot square plus v of phi. and p of phi is half phi dot square minus v of phi. Now, in order to find the equation of state, omega phi is always defined as half phi dot square minus v of phi over half phi dot square plus v of phi. Now, one of the crucial thing I want to show that if omega phi, what is the greatest limit of omega phi? This turn out that if v phi is dominating over the kinetic part of the field, because phi dot square is the kinetic energy of the field. So if potential of the field is dominant over kinetic energy of the field, then you can see that v of phi over v of phi, and this is turning out to be negative of 1. So now the quintessence field, no matter how much you increasing the energy of the quintessence field, it turns out that omega phi cannot go beyond -1. But in order to surpass, or in order to quantify the Hubble parameter, or in order to increment the value of Hubble parameter, you must go beyond -1. Means that there is a reason. So there is a negative of 1, and when you are increasing from, let us say, -0 to -1, it is called accelerating region. Okay, from the perspective of omega, which is equation of state. And when you crossing this phantom barrier, which is the negative of 1, and this is called the phantom field, or phantom region. Okay, so there is an acceleration. This is also an acceleration, but it will go like minus of infinity, -2, -1, -3, and so on. So we see that there are two things that is happening. One thing is that equation of state must go beyond -1, which is -1.2, 1.3, -2, and so on. And on the other hand, although we can increase the energy density of the field, and after increasing the energy density of the field, if you are talking about the normal quintessence field, it will always it cannot go beyond -1. So what we require to do, we require to use that, okay, we require some phantom field. Now in this paper they have taken this thing using some different idea. So you have to take the phantom field. Now phantom field is written by half phi dot square minus v phi, plus v phi, and over here you can see that p phi is equal to -half phi dot square minus v phi. So using this phantom field, if you find the equation of state, this equation of state will turn out to be half phi dot square minus v phi is equal to -half phi dot square plus v phi. So what you are describing that, okay, there is the potential is always there, but the kinetic part will also contribute. So because of this negative, this can become lesser than -1. Lesser than -1 means that it can go -2, -3, and so on. So now, how can we see these two effects in one way? So for that purpose, what they have used, they have instead of using different fields, let us say you have to use quintessence field, which is normal quintessence fields, in which I have already shown you that it cannot go beyond -1, and you have to use the phantom quintessence field where it can easily go beyond -1. Okay, so it cannot produce the accelerating solution. So in order to quantify these two things, you can use that, okay, I'm not going to use any kind of field. I can just parameterize my omega of a, can be written as omega 0 plus 1 minus a into omega of a. Now based on the choice of omega 0 a, if you consider that omega 0 can be let us say -1.2, and whatever the omega a, you can turn out that it will become phantom, and similarly something. Now they have used the two different parameterization. One of the parameterization is called the CPL parameterization, and another parameterization is called omega CDM parameterization. Here WCDM parameterization is shown that it is not lambda CDM. A lambda CDM equation of state is always negative of 1, but WCDM equation of state is just omega. So in this omega, it is the function of time. So omega can be -1, -0.9, or maybe -1.2, whatever you can say. So now first they have shown you that if I am using model omega CDM, okay, and using this, they have considered, okay, there is a Friedman equation, kappa square, rho radiation, rho matter, rho of lambda, and rho of, let us say, phi. So this phi is basically given by omega CDM. Now how they have incorporated this thing in their study, let me show you just in a simple way. Okay, when you try to measure, so it depends on the measurement. Okay, so when you try to capture the cosmological data, when we are trying to measure the angular diameter distance. Okay, so we have the sphere of the CMB spectrum. So this is kind of a sphere of the CMB spectrum, and from there we try to see the patches. Okay, and these patches are determined by the angular diameter. That what is the angular diameter? What are the angular diameter and so on. And when they are, this angular diameter is turning out to be 1 over h0 1 plus, let us say we are, so in the matter epoch, when the universe is going from radiation to matter phase, it was corresponding to z is equal to 1100 or maybe 11,000, whatever. So it is determined by z star. So in the recombination epoch, let us say at z star, 0 of z star dz over e of z. And what is e of z? We usually write h of z as, let us say, h0 times e of z. Okay, so basically you can just think of it, the Friedman equation, as if the 3h square, I can simply write h square is equal to h0 e of z. So e of z has all these components and so on. So now what you can see, that there is an integrand over here, and this is constant. Now if your h0 has to be increased, and dA, let us say we are talking about that in the last in the epoch of recombination, means that when the radiation and the matter, they are at that stage, there will be some phase transition, and during that stage, at that state, during the energy density has to be, same, or have to be equal, isn't it? That is the called of recombination epoch. So during that period, dA is proportional to 1 over h0 1 plus z. So the thing is that at that epoch, or at this fixed z star, your dA, the angular diameter distance, has to be constant. Now we want to increase our h0. Now in order to increase our h0, this integrand has to be increased, because they are in fraction. So this is like dz over ez, and over here h0. So in order to produce the constant ratio, if it is increasing, therefore it will also increase, and if it is decreasing, then you have to also decrease this integrand. And so what they have done is that, okay, we can write dz over e of z as an a star, okay, at the epoch of recombination. So your dA is fixed. Now we want to see that how this will vary. So over here, they have shown that. Now here you can see in the figure that they have computed AZ star with the omega of lambda. And this omega lambda is simply, you can always write omega of lambda as. So I can also write here that 3h square, okay, 1 is equal to omega radiation, omega matter, and let us say omega of lambda and omega of whatever the W and so on. So I can compute this omega lambda in terms of these candidates. Okay, now, so what they have analyzed is that, okay, they have plotted AZ star over omega of lambda, and they have also plotted this lambda CDM. So for the lambda CDM, since the equation of state is not varying, so it is turning out that this is the solid line. On the other hand, we have two different lines. So you can see that this is the top of the line where there is a dash and dot. So this dash and dot for the phantom line, where your omega has been taken out minus 1.1. So when you have taken omega is equal to minus 1.1, this is the region that they have shown. And when you have omega is equal to minus 0.9, when it is the accelerating epoch, this is the radiation. Now what we are argument is that if you want to increase your h0, A star has to be increased. The A star has to be, go beyond the lambda CDM model, what they are saying. So here what you can observe is that if you want to go beyond 3.20, then omega lambda has to be negative values for AZ star. And for this reason, you can see that this is giving you the largest value, and omega lambda has to be negative. And this is the line that it is showing you, this one. Now omega lambda is 0.7 at present time from the lambda CDM model. So here it is the point here where you can see that it's a 0.7 omega lambda. The cosmological constant, or omega dark energy, has to be 0.7 or 70%. So this is the point at which all the three components are coincide. But AZ star can have the positive values or more values, for omega lambda is negative 1. On the other hand, if you just using omega to be minus 0.9, you can see that this region is falling in the lesser value, Az star is 3.0, 3.15, and for here, this is the one a dash line shows. So now when how you can increase the Ez and H0 for this non-phantom case or for the accelerating case, you have to choose omega lambda to be positive values, so it will take more positive values, and then Az can become positive. On the other hand, if you go beyond omega lambda, which is greater than 1 and 2 and so on, then Az can be this one. So the thing is that omega lambda or omega dark energy cannot go beyond 1. So here we can see that if you have to be -1, okay, omega lambda can be -1 and so on. So we can see that this is the reason, this is the preferred reason where Az star is taking the positive values. Okay. So now they have also used this analysis and plot that what is the equation of state, because we have already seen that equation of state is omega CDM, and we have plotted with omega of lambda the equation of the vacuumed energy. And they have seen that the solid line is representing Z is equal to -0.38. Dot dash lines are for DL at luminosity angular distance at Z is equal to 0.5, and dotted for angular dA at Z star 1100. So from that, what they have found is that this omega lambda, when they have the negative values, then omega is in the phantom region, and when omega lambda is the positive values, then it is moving in the non-phantom region or accelerating region. So in some sense, it shows that if we want to produce the anti-de Sitter kind of acceleration, or the whatever the omega lambda is negative, then it will automatically go in the phantom region, or for the positive values, it will never go into the phantom region, it will always go into the accelerating region. Okay. So this is a very interesting studies that how we can analyze, how we can increase the value of H0 and so on. I think you understand this preliminary version. So in the later on video, we are going to discuss more about it, that how we can what this data has already told about many different scenarios when they have studied this data with the CMB data, CMB bow data, CMB bow plus H0 data, and similarly they have given some result, and what they have found we will talk about in the next video. So thank you very much. This is the Ananda Cap signing out.